Okay, now finally, after doing all this groundwork, all this foundational work, we can finally bring it all together into some actual physics here, and finally state Newton's second law for rotational motion. Okay, so we already know Newton's second law for regular translational motion is, of course, F equals ma. And we've also learned over the last, quite a few videos that the rotational version of the acceleration is the angular acceleration, and the rotational version of mass is moment of inertia, and the rotational version of force is torque. So it should not be surprising that the rotational version of F equals ma is tau equals I alpha. So just as forces cause changes in the translational motion of the object and the mass resists that effect, torques cause changes in the rotational motion of the object and the moment of inertia resists that effect. So it's exactly the same idea, just everything is translated into rotational variables. Now, how do we actually apply this to solving problems? Well, the procedure is very much analogous to how we solved F equals ma problems, except now every step of the process is kind of a little bit more complicated. So step one, we need a free body diagram. So this is the same as the F equals ma case. Just take note that your free body diagram should now include where the forces are acting, in addition to the information that had to be in there before in terms of the magnitude and direction of each force. We have kind of a second step beneath that, which is new, which is that you also want to make note of the axis of rotation about which you are doing all of these calculations. Because we saw, remember, that the axis of rotation is important for calculating moment of inertia, it's important for calculating torque, and of course the concept of alpha doesn't make any sense without an axis of rotation either. So make sure you know where your axis of rotation is located. I like to mark that with an X in the picture. The next thing we do, and this is something we didn't have to do in the old cases, normally what you're given in these problems is not the torques, normally what you're given is the forces. So the next thing you'll need to do is convert all of your forces into torques using the force component or lever arm method that were described in the last few videos. So then you've got a bunch of torques. Just like with the case of forces, you're going to need to sum all those torques which are acting on the object. You want to sum all the torques that are acting on the object, just like before we had to sum all the forces acting on the object. Tau here in tau equals I alpha represents the sum of all the torques, not just one torque. Number 5, you may need to calculate the moment of inertia. Depending on what the problem is you're solving, you might need to just look it up in a table, and or you might need to apply parallel axis theorem. Okay, and possibly apply parallel axis theorem to move the axis. Okay, now you've got your tau, you've got your I, then finally you can apply this equation to obtain the rotational acceleration or the angular acceleration alpha. So that's the procedure. I hope it looks to you very analogous to what you were doing in F equals ma problems. If you see the analogy with F equals ma problems, this won't be too bad. You have some extra things to worry about. Calculating the torques is not trivial, as we saw over the last few videos. Sometimes calculating the moment of inertia is not trivial, but if you can master those individual elements of the procedure, here you're putting them all together into one single unified problem-solving approach. And that's going to be the main idea for solving all the problems over the next several sections of the course.